Today I will cover chapter 5 and 6 together because actually they are not separate topic. They should be integrated a single theme. Otherwise, your understanding will be fragmented. You cannot develop full understanding or simple understanding. If things are presented separately, you may have lots of details, but you will lose the forest. You cannot get the core concept. Core concept is like this: dual space concept. So, from the first chapter, this is part 3, fundamentals of protein crystallography, but in the essence, it's not specific to protein, but also fundamentals of crystallography, just fundamentals of crystallography. This is not specific to protein. Protein is unique because we have a single isomer. What is peptide? L or D in nature? L. Because of such a nature of amino acid, we have all L forms. So it's not in central symmetric. Central symmetric itself is a kind of crystallographic terminology. It cannot have inversion related pair in terms of packing or in terms of appearances. So because of that, it can be called fundamentals of protein crystallography, but symmetry relations and Fourier transform relations are also valid in all crystallography, not only in protein crystallography. Take such things in your mind. Also take these two words, Fourier transform and reciprocal relation. But I will give you capture or reminder from chapter 1, introduction, in terms of terminology. But anyway, before that, I'd like to remind you table. We will discuss this table at the end, but take notice of these two. Column, this column and this column. Right now, I'll not describe anything at the top, but look at these two columns. What do you find in terms of symbol? It's a symbol. In terms of number, which numbers do we have in this column? 1, 2, 3, 6, not 5. 1, 2, 3, 4. You missed 4. Okay. And what else do we have in this column? M. Yes, mirror. M stands for mirror. What else do we have? Bar. Inversion. Okay. So that's all. We have something else in terms of symbol. Slash. I'll explain slash later. Okay. But anyway, the meaning of 1, 2, 3, 4, 6 and meaning of bar may not be understood with common sense because this is peculiar to crystallography or strange to novice. Now you have something in terms of crystallographic vocabulary. Here, if you look at the other column, what do you have? These are numbers of space groups. So regardless of parentheses and numbers there, parentheses, what do you have in terms of symbol? P, C, R, even here I, at the end of beginning of such a symbol. That is lattice symbols. And what else do we have is more like here, numbers in terms of 1, 2, 3, 4, 6, but we have some subscript. Okay? Regardless of that, we do not have anything new, but here we are missing something. Unlike here, what do we miss here compared to here? M. No M there. Even we are still missing something. Slash. Comma. Comma is not here. So bar and slash are not present here. You are very correct. So I'll tell you something in advance. Here, it's called chiral space group. That is unique in, that is not unique in protein, but that is because of uniqueness of protein composed of L amino acid alone. Because of L amino acid and its peptide, we do not have M or bar or slash, because bar is related to inversion, M is related to meter, and slash is something else. Okay. To have slash, we need to have meter. So slash means a meter perpendicular to previous axis or main axis. Because of that, slash is related to meter. So as well as a result, meter and inversion are not present in the space group of protein crystals. That is kind of a main difference between other, not other, crystallography general and protein crystallography specific. Okay? Anyway, from this to there, we have data collection to get the data out of crystal, and this is what it had at the beginning. To do protein crystallographic analysis, we should have something. What is this? Crystal sample mounted on top of goniometer head. And what is this? Detector. Usually CCD detector at synchrotron source and image plate detector at our home source. And a detector. Saba, how do you see your proteomic analysis in terms of 2D gel?
In 2D gel, we see the spots.
You see the spot?
Yeah.
In terms of PI and in terms of molecular weight, you have kind of
distribution
image,
spots, yes.
2D image. Like that, we have two-dimensional image at each rotation angle, but unlike your 2D image, here we have origin. Also, we have some symmetry relation around the origin. That is what is common between your 2D image in protein analysis. Like anyway, we should scan the result, or we should detect the result in terms of rotation angle, or your case in terms of variation of your sample according to different condition. But this is systematic investigation of reciprocal space or sample space using two-dimensional detector. As a result, we have something systematic. So we have some intrinsic symmetry. In your 2D image, you do not have any symmetry. Your each spot has characteristic PI and molecular weight, but all spots are independent of each other. But here, spots are not independent. They are related with some geometric arrangement. So that is called structure factor in terms of HKL coordinate in A star, B star, C star space, reciprocal space. If we transform such data into electron density in real space, we have electron density quantum map like this, and we can develop model like this. That should be our end result after crystallographic analysis, and that is experimental data. Actually, on each spot, we can get numbers like intensity reading of your two-dimensional gel image. But unlike gel image, we will have a digital image of X-ray diffraction, and we will convert such an X-ray image into single number. Each spot will have some number corresponding to FHKL. And a Fourier transform, we have FHKL data, and with such a data, we will calculate electron density function, and based on such an electron density function or quantum map, we will develop a model like this. So electron density and structure factor FHKL are related with Fourier transform. That is the result of that is the key relation in crystallography. But here, what do you have in terms of coordinate? We have two coordinate systems. In terms of vector, A, B, C, and what else do we have?
A star, B star system.
Yeah. A star, B star, C star. I'll tell you how they are related later, but right now, please keep these things in your mind. We have two coordinate systems, A, B, C, and A star, B star, C star. They are related with which relation?
Reciprocal space.
Yeah, reciprocal relation. Do you know the word reciprocal? What does that mean to you?
Inverted.
Inverted. As a result, if we multiply both number or both vectors, what do we have?
Cancel. Null.
In terms of the word reciprocal, if you have x and multiply 1 of x, that will result in 1. Likewise, if you have A star and A, this will result 1. That is the definition of reciprocal. But here, these are reciprocal numbers. But here, reciprocal vectors. We have difference in number and vector, but in terms of role and in terms of meaning, they are the same. Reciprocal is like an inverse number. Reciprocal vector is a kind of inverse vector. But rather than calling them inverse vector, we use reciprocal vector. Okay. And here, what do we have? What is these and what are these?
Electron density.
Above is
Electron density.
electron density and model fitted inside of electron density. Not only electron density contour labels are drawn with grid, and inside of such electron density, stick models are drawn with overlapping. And here, what do you have?
Fourier transform
Diffraction data.
and scale.
Both are valid. These are Fourier transform pair of the above data, and they are related with Fourier transform. But here, what did you say, Muhammad?
Diffraction data.
Diffraction data. Also, these are diffraction data drawn in reciprocal coordinate. For example, we can say these are this direction A, this direction B, but in the text it was not specified, it was not given properly, but we can assume A, B, orthogonal C. Or in orthogonal system, A star, B star, C star are in the same direction. Otherwise, we have some tilt. Okay? Only in orthogonal condition, length of A and length of A star. What is length of A star in orthogonal system, Muhammad?
One over A.
Yes, 1 over A. B star likewise 1 over B. C star 1 over C. So simply A star equals 1 and B star equals 1 and C star equals 1. That is the definition of reciprocal number in mathematics and reciprocal vector in crystallography. But reciprocal vector is three-dimensional entity, so we should consider them either in vector form or in length form. Here I wrote them in length form because these are simply numbers. A, B, C are in numbers. But here we have three pairs of reciprocal and real space representation. What are differences between these three?
Resolution.
Yes. Where do you have resolution and what resolution are you looking at?
Angstrom.
Yeah, angstrom was given. In terms of symbol, resolution symbol, like A, B, C, A star, B star, C star, we will use D and D star. D and D star. That's the symbol we will use. And what is the result of different resolution? How resolution in reciprocal space affecting resolution in real space? This time, don't me. This is kind of observation and your guess.
The first line is different in electron density, and I think the picture number 3 is higher higher electron density than.
Which one is high? This side.
Yeah.
Better density or higher resolution?
Higher.
Higher resolution.
Yeah.
Higher resolution, you said.
Yeah.
For higher resolution and lower resolution, medium resolution,
The
it's
first
okay.
is the higher electron density, and the second line is the higher resolution.
So it's correct to say higher resolution here, medium resolution, and lower resolution. So it's good way to distinguish the above 3. But what do you have in the below 3? Higher resolution, medium resolution, lower resolution. What result do we have in reciprocal space or diffraction data, as Muhammad told? Difference.
We have more data.
More data in higher resolution and medium amount of data in medium resolution and less data in low resolution. So in return, low amount of data result in low resolution. Higher amount of data will result in higher resolution. Okay. So this is in diffraction data space. This is in the result, our result. To get higher resolution, we should collect more data. But to collect more data, crystal should reflect better or more. More means, if you look at numbers given as resolution, this is a larger number, this is small number. That is D in angstrom, but if you have D star, what will happen? I'll give you some hint. D multiplied D star will be 1. And so here, let's take 2 angstrom. What is the reciprocal number of 2 angstrom?
1 by 2.
1 over 2 is 0.5 reciprocal angstrom. But what will this be?
1 by 3.
1 over 3 is 0.3333 reciprocal angstrom. So in terms of D star, this is lower or smaller number, this is bigger number, this is much bigger number. I'd like to help you develop sense of reciprocal relation in resolution. Resolution in terms of symbol D can be also used in symbol D star, but D and D star are not independent. They are relative with this simple relation of reciprocal number, like x and 1 over x. Simply D star is 1 over D. If you know D, we can calculate D star just by inverting the number, also inverting the unit. unit in D is angstrom and unit in D star is reciprocal angstrom, but it's cumbersome or it's too not too difficult, but it's not easy to pronounce reciprocal angstrom each time. Also, we know this kind of simple relation. So when we talk about resolution, we always talk about resolution in terms of D, not in D star, by convention, not to be confused or not to introduce any kind of extra difficulty in terms of pronunciation. So if you think in terms of resolution in D star, this side is high or bigger number, so better resolution and higher resolution. So only in this star term, actually high and larger corresponding and low and smaller are matched. Okay. Also, in terms of data amount, it's better to have such an idea to collect higher resolution data. Higher resolution data demands more data. Even proteomics, to have better coverage of protein expression, we should get more spots. That's the whole purpose of your improving your effort to improve 2D gel. Otherwise, you have just few spots. It's hard to discern the difference to proteinic changes. Okay, so to know the differences in structure, it's okay to have this kind of crude image if you are interested only in folding. But if you are interested in drug bound to target protein, it's better to know higher resolution data. Okay, so this side, more effort, less effort, better crystal, worse crystal. Okay, it's about reciprocal relation in resolution, also reciprocal relation in between real space and reciprocal space. Okay. So this is again in mathematics form. Here, real space electron density and diffraction space intensity or diffraction data space, as you said. So here, what else do you have? FHKL. FHKL itself is a complex number, but to represent such a number in three-dimensional space, or particularly here, two-dimensional space, we are not dealing with FHKL directly, but we are dealing with FHKL magnitude squared, or simply intensity. Okay. Up to here, any question in terms of my reminder? Fourier transform and reciprocal relation, and you have some pairing. For Fourier transform, what kind of pair should we have in our mind? Pair.
Electron density and diffraction data.
Yes, electron density and diffraction data, or simply FHKL. Okay, FHKL and rho XYZ. We should have such a pair promptly in our mind. Fourier transform, these two are related. And in terms of reciprocal relation, what do we have in terms of pair? For your reminder, I'll go back here. I'm talking about pairs you should have in your mind. In terms of Fourier transform, F and rho are related. But in terms of reciprocal space or dual space, what do you have in terms of pair?
ABC and A star, B star, C star.
Yes, that's right. But let's give some initiative for other two. So you are so key. So these vectors are related with reciprocal space concept. So far, I didn't talk about anything in symmetry. Now I will talk about symmetry through crystal geometry and diffraction basics. But before jumping into symmetry, I'll show you again this again. Here, what do you have in first column in terms of symbol?
ABC.
ABC,
Alpha, beta, gamma.
That's all. And in terms of numbers, we have 90 degree and some equality and inequality relation, also 120 degree. Okay, kind of magic angle or specific angle, which result in some packing constraint. Okay, nothing else. So in terms of symbols, also in terms of number of symbols, we should learn very limited in crystallography, not very much. Isn't this strange? In this paper, we are talking about difficulty of crystallography. Also, it is called a peculiar science. But it's true, it's peculiar because it is using, crystallography is using common symbols like 1, 2, 3, 4, 6, not as number, but as something else. What is something else? 1, 2, 3, 4, 6. Actually, those are numbers for computation. But here, 1, 2, 3, 4, 6 are not used as numbers for computation. They are used for something else.
Space group.
space group.
Yes, you need to calculate. Space group symbol, they are used as part of space group symbol. Even here, Laue group symbol. You took space group symbol here, but here also they are used as a part of Laue group symbol, even though I didn't explain anything about Laue group. But if you look at here also, we have 1, 2, 3, 4, 6. These are called point group. So also here, you look at minimum internal symmetry. Now focus on first and second symbol. This is about cell parameters or lattice parameters. As you said, ABC, alpha, beta, gamma. Here, these are also description about crystal system composed or defined by ABC, alpha, beta, gamma. But if you look at this column, first one is the name of that is triclinic. There, we do not have any internal symmetry. Then, at the monoclinic, what we have? Would you?
Two-fold rotation.
Yeah. Here, two-fold rotation parallel to unique axis B. So, 2, 2. Now, Saba, what does this mean? Here, 2. Number 2 from 2 over m, or here simply 2, does not mean number 2 in arithmetics. What does that mean in crystallography? You have some cheating or hint here.
Two-fold axis.
Yes, simply two-fold
Rotation.
axis or two-fold rotation axis.
Yeah.
Then let me ask you, 도띠무이, 무이.
Yeah.
Here, 4 over m, or simply 4, what does number 4 or symbol 4 mean?
4 is the four rotation.
Yes, correct. So, symbol 4 is not number 4 in mathematics. Symbol 4 is fourfold rotation symbol. Okay. Likewise, symbol 2 or number 2 is not number 2 in arithmetics, but twofold rotation symbol. Okay. Likewise, what is 3 and 6, Muhammad?
3-fold and 6-fold rotations.
Yes, yes. But why don't we have 5-fold or something else in crystallography?
Because there is no 5-fold rotation.
Yeah.
Actually, we have 5-fold rotation, but we do not.
I think 5 is not symmetry. 5 is not
Symmetry of what? Oh, nice, nice gesture articulation.
One is the symmetry,
Mm.
and 4, 4, 3, 3 connect together to make 6. In 5, there is no
No matching
symmetry.
in space
And
for packing. Yeah. That's true. Generally, number n in general, 1, 2, 3, 4, 5, 6, even up to infinite, it can be rotation axis symbol. Point group is okay, but space group is not compatible with allowed packing in 3-dimensional space. Because of that, we do not have number 5 symbol or higher numbers symbol in space group. But point group, or for a general case, not specific to protein crystallography, you may be able to use such a symbol, but that's not for protein crystallography in 3 dimensions. Any protein crystallography in 3 dimensions, okay? We are limited in terms of symbols allowed for space group for protein crystals, okay? Now you have idea about number 1, 2, 3, 4, 6, and now jump to this thing again. Crystal geometry and diffraction basics. I tell you something about symmetry and scattering. These are two different words, but they are related in some way with Fourier transform and reciprocal vector or dual space. First of all, what does that mean? Geometry. The word geometry.
Sequence.
Sequence. Geometry is not about sequence.
shape.
Shape determined by ABC, alpha, beta, gamma. Packing shape. So, packing shape. Okay. Through crystal geometry, we are concerned about A, B, C, alpha, beta, gamma, which defines the packing unit. Okay. But we are not interested in packing itself. What is our primary concern in terms of protein crystallography? We are not concerned about packing. We are concerned about structure. Where does structure come from?
From diffraction.
Yes, from diffraction. So we will talk about diffraction under the light of scattering. So symmetry, scattering, we look at with the help of dual space concept. Okay. Dual space concept, before jumping into dual space concept, I will ask you some. Let me write down something here. Rho x, y, z, and here f, h, k, l. Symmetry. Symmetry in these two functions. So, firstly, we are not concerned about symmetry in electron density and symmetry in FHKL, but what do we have any out of our experiment? 1, 2, 3, 4, 6 compatible with space group of protein crystal. Here, we will have some packing compatible of this kind of rotation. And what will happen such a packing, what will happen in terms of F? That is the symmetry concept in crystallography. So here we have space group. Here we have Laue group. If I tell you the result, I'm not so in terms of I have some difficulty to explain this concept, but please forgive me at this moment, but I'll make some rearrangement. FHKL, in terms of experiment, I'll explain from the workflow of experiment rather than theoretical point of view. Here in the text, they are explained in terms of theoretical consideration, but I'd like to explain them in terms of actual experiment. What I'm trying to tell you is, in the textbook, the story is given for, let me talk about this first. We have training for engineer, and I'm talking about car. We have training for engineer. Also, we have training for driver. There is difference between training for driver and training for engineer. For training for engineer, I'm talking about car builder. We should learn the combustion for engine, also mechanics for steering, also some electronics for navigation. We need to know all the details. But for drivers, what should we know? For driver's license, not engineer's certificate.
How to drive.
How to drive. But basically, we should know the handling, also changing the gear or acceleration. Most important is taking brake, nothing else. Oh, also traffic signals, regulations. Okay. Likewise, not to develop computer software for crystallography, not to develop some new theory in crystallographic phasing, but to use crystallographic data for your own purpose, or just to understand colleagues' lab meeting presentation. Okay. In that regard, I will talk about this. Firstly, in terms of data, as your 2D image, we have FHKL data. Then we will have electron density model building. This is like your 2D image, and this is like your ID. Did you do mass spectrometric analysis?
I have given, but I haven't got the results yet.
This is like a 2D image, but this is like your protein ID. Each spot will result in identity in NCBI database. Okay, you will have some list. Likewise, we start with not with electron density, because this is our purpose. If you have this data, we don't need to have protein crystal and difficult experiment like diffraction. So we start with FHKL. From HKL, we always have symmetry. That is what I'd like to tell you. Normally in the textbook, they start to explain symmetry starting from electron density or crystal packing. But I'd like to talk about symmetry starting from diffraction data. Here, electron density, regardless of space group, we always have some symmetry in protein crystal. What symmetry do we have? This case, Muhammad. Intrinsically, we always have symmetry. If we are saying crystal sample, always we have symmetry. What symmetry do we have? This may be difficult for the other two, so I'm asking you. You have some basic knowledge of crystallography. Even you can answer we.
I guess.
Yeah, guess.
But maybe we have a square. A square, it means four-fold rotation.
That is kind of extra because we can have one.
One square,
Hexagonal is 6. Trigonal is 3. Tetragonal is 4.
Cubical.
I'm talking about basic symmetry, intrinsic in all kinds of crystal. If we are talking about crystal, sample can be either non-crystal or crystal. If the sample is really crystal, we should have some intrinsic symmetry built in. I'll give you answer in terms of ABC. What do we have? Packing. Here I followed textbook story, so I do not have any packing here. But in the text, they are talking about some packing through ABC. Let me show ABC. Let's come back to ABC. Here, this is one unit cell of crystal, A, B, C. But if you are talking about crystal, this is one unit cell. How many unit cells should we have to be a crystal? This is kind of...
At least one.
One is not a crystal. This is kind of open question or challenging question in terms of your literacy. Anyway, this is one unit cell. To be a crystal, we should have some periodicity. If you have periodicity along one direction, that will be called one-dimensional crystal. If you have periodicity along A and B in plane, it will be called three-dimensional. To be two-dimensional. To be three-dimensional crystal, we should have periodicity along A, B, C altogether. Okay? So in theory, it can be infinite along A, infinite along B, infinite along C in terms of repetition. So in theory, it can be infinite. But to be practical, we should have several along A, several along B, and several along C. So to be several, at least even for smallest one, in practice, what was the size of your crystal? You didn't have any crystal, but last time when I talked about protein dimensions are about several 10 angstrom. If you have several even now we are talking about ABC. A to be compatible with that diagram. So I'm talking about symmetry of any crystal, not particular to protein crystal. So any crystal can be described with ABC, A, B, C, and Now I'm talking about typical dimension of protein crystal sample. Let's say typical dimension is 0.1 millimeter. Okay. Also, typical dimension of A, for simplicity of calculation, let's say 100 angstrom, which is 10 nanometer, right? Then how many copies do we have along A? If we are saying A equal to 100, which is 10 nanometer, is that correct? 10 nanometer? And 0.1 millimeter is 100 micrometer, then 100 and 1000 nanometer, right? How many copies along A in this case? V.
10,000.
Yes, 10,000. Okay. So, to be a real crystal like this, one of the such a crystal dimensions, if it is 0.1 millimeter, quite visible under microscope, but nearly invisible with our naked eye. This is the limit of our naked eye. Okay? This is kind of microscopic size. Already, for such a small, tiny crystal, we already have 10,000 copies along A. Not only along A, we should have such a repetition along B and along C. So if we are saying these copies along A, then they should be tripled. So 10 to the 4, 3 times is 10 to the 12. Huge. If you use much smaller one, this side, let's say just 10 micrometer, which is marginally detectable even with strongest synchrotron radiation, then this will be reduced by 3, and that is still billion copies. Billion copies. You should have billion copies of this to be smallest crystals which can be utilized for your diffraction experiment. So here, now come back to symmetry. What symmetry do we have? To be cubic, A, B, C should be equal, and alpha, beta, gamma should be 90 degree. Here, by accident, they are drawn like cube, but they are not really. This is not really cubic. So, if you are talking about cubic, among 1, 2, 3, 4, 6, you are talking about 3, 4 combined as a cubic. But simply here, we do not have any rotation symmetry. We just have something else in terms of symmetry. Now I'm asking you again, Muhammad, what symmetry do we have here?
Alpha, beta, gamma.
No symmetry in alpha, beta, gamma. No particular constraint in alpha, beta, gamma. Let's take this as a triclinic system. One alone. One means, here, one means no symmetry at all. But in terms of symmetry, inside of unit cell, we have one. One means no symmetry, no rotation symmetry. But still, to be crystal sample, we have symmetry of at least billion copies. What relations do we have with these billion copies of molecules at the size of 10 micrometer of unit cell length A equals 100 angstrom, ABC 100 angstrom. This is important as a cornerstone or baseline of your understanding crystallography. So I'm spending time for you to grasp the idea behind this. If you miss this, your understanding of crystallography is like a sand castle. if you have wind or difficulty or complex situation, you may not grasp the meaning of crystallographic data. But if you have this understanding or understanding the core concept like this, your understanding of crystallography will not be collapsed. You will be a competent driver, although you cannot be an engineer of the car. I'm challenging you. Muhammad, particularly. I'm waiting for you to answer the right answer.
Okay, we have relation of point groups.
No relation connected point group. Point group is 1, and actually 1 means no extra symmetry. But if you are clever with 1, what space group symbol do we have for corresponding point group 1? Let me go back here. At the beginning, I showed you this. Here, minimum internal symmetry. What do you have at the first row? None. But there, what they are talking about in terms of symmetry, they are talking about internal symmetry. What internal do we mean here? Internal in unit cell. No internal symmetry within the unit cell. But still, external symmetry we still have. Such external symmetry I'm talking about now, Muhammad. Look at the first row, no internal symmetry, so
Rotation.
Rotation cannot be this case. Anyway, let's look at the symbol here. 1 and corresponding P1. Space group for triclinic is only 1 in crystallography, that is P1. Then let's talk about symbol P. Let's figure out the difference between point group 1 and Rabi group 1 bar and space group P1. Let's focus on very basic of crystallography, because this bottom line symmetry present in all kinds of crystals if we are talking about samples in crystal form. Today I will not talk about higher symmetry 2, 3, 4, 6, but I'll focus on difference between 1 bar, P1. That is the very basic of crystallography. So if you figure out 1 bar, P1, we are done today. Then I'll talk about the other thing next time, next week. So, not to spend too long time, I'll give you answer. Is that okay? Especially for Muhammad, I don't want to put you in much frustration. Anyway, I'm talking about symmetry of any crystal. I did say any crystal. Any crystal, general crystal is like this. Triclinic. You can describe any crystal in terms of generic ABC, alpha, beta, gamma. Saba, you talked about cubic. Yes, it was drawn like cubic. Even to me, alpha equal to 90 degree, gamma also 90 degree, beta it seems to be 90 degree. But those are drawn in general case to explain the concept of reciprocal axis, even with hands like this. We cannot be in perfect 90 degree. Even our fingers are not in same length. So they are in general case. Although the left side were drawn in similar form to cubic or orthogonal. Okay, if you look at right side, these are really general case. ABC not necessarily equal to the same length. Alpha, beta, gamma not necessarily equal to 90 degree. So they do not have any particular constraint on ABC length and alpha, beta, gamma angles. Okay, But it's called 1 in terms of rotational symmetry of unit cell, and 1 bar in terms of its Fourier transform pair, electron density, if you have something inside of this. Then we have space group symbol for this one, general case, P1. P1, P, symbol P in P1 means what? P.
What space group?
P stands for primitive. C stands for C centering, and F stands for phase centering. So P means no centering, or just primary or primitive. Okay? It's better to know what the symbols mean. Also, it's better to know the pronunciation of each symbol. This case, P1 can be space group this one, and as I told you, now I'm giving you answer. Symmetry intrinsic in any crystal. It was not rotation, because 1. P1 for that symbol, that case is P is primitive, but even primitive without having centering, but we always have translational symmetry. Translational symmetry along 3 axes, not along any other axes. We may not have such a symmetry along this kind of orthogonal case. No symmetry in between. Okay? Other directions, we do not have such a symmetry, but only through A, B, C, we have repetition. Like a periodicity in time, we have periodicity in space. So we can define such a symbol with A, B, C direction, with the length of A, B, C in italics. Here, vector A, B, C written in boldface. If we are saying italic A, B, C, they are length. Okay, length of periodicity, length of vector is periodicity along that direction. Now you have an idea about symmetry, right? Now I'll give you a chance. What symmetry intrinsic in all crystal?
Translation.
Translation along which direction? Saba. We have 3 directions. We should say such a 3.
Primitive.
We, your turn. In which direction? Translational symmetry along.
A, B, C.
Yeah, that's it.
Only
A, B, C. Okay. But because A, B, C are not position but direction, we can have arbitrary origin. I'll not talk about arbitrary origin further, but we have some arbitrariness upon the choice of origin. Okay? If we translate ABC along any direction along ABC, it can be ABC. Vector is vector. Vector is not position. So we have freedom in terms of choosing the zero position. Okay? They are flexible or floating, so-called floating origin. So when you determine crystal structure or determine electron density, we should pick some point, not to have floating model. Otherwise, your refinement will be floated along ABC. Okay, you should fix one of them. Anyway, from now on till the end, I will not talk about 2, 3, 4, 6, but I'll talk about the relation between 1 bar, and P1. Okay? Especially 1 and 1 bar. That is inversion, or simply addition of inversion, central symmetry. Let's have some break. 2:30. Muhammad, did you read this paper?
I just read first and second page.
No. First and second page will be fine. But I will not read this paper today, but don't take this as a mathematical exercise, but take this paper as an exercise of your English. Approach this paper. Yeah, vocabulary. First of all, at the introduction, crystallography is a peculiar science, that what I talked about. You should understand the meaning of peculiar. In this case, for me, to exaggerate the meaning, crystallography is an uncomfortable science because it is using the basic vocabulary in mathematics in different ways. That is kind of twist. Also, something is not explained properly in the textbook. Something is explained, but they are not integrated very well. So you need to have a basic understanding, not distracted by something extra. You should be fully compatible with basic. Okay. Let's talk about basic concept again. So let me come back to beginning. Here we talked about electron density and diffraction data, FHKL, in terms of symbol, electron density rho, XYZ, and intensity HKL. Okay. I told you we are not starting the experiment with electron density because this is our target result. This is our beginning. Although textbook is talking about protein structure, what we are dealing with initially is crystal sample. Okay? Starting from crystal sample, we get diffraction data. Okay? Here, if you look at these two simple images, we do not have any symmetry here. It's like one in 2 dimensions. But already here, we have something more. Particularly, this has more symmetry because we are looking at some part of protein structure, and full unicell may have higher symmetry, but here always we have inversion, although it doesn't have any symmetry higher than 1. Okay, that part I will talk about. Also here we will have translational symmetry, but the other side, diffraction data, we will not have such a translational symmetry. Translational symmetry is always present in not unicell, crystal, made of several billion copies of unicell. That is the point you missed, Muhammad. So we should not miss the concept of translational symmetry present in all kinds of crystals. If you are saying, or if we are talking about crystal as a sample, always we have translational symmetry along A, B, C directions. Then we have diffraction pattern because of such many copies, much more than billion copies. I will not talk about Fourier theorem, Fourier convolution theorem in crystallography, but if you have electron density or simply protein inside of one unicell, coupled with translational symmetry over such a billion copies, then we have diffraction pattern like this. But unless we have such a billion copies, we will have some blurring. Resulting pattern will not be spot like this, but continuous form. such things are explained in chapter 6 of textbook. But to follow such an argument, it's more about physics and mathematics. But we do not understand such a physics and mathematics to know only this end result. End result is like this. Translational symmetry or duplication over billion copies will result in spot. Otherwise, we will not have spot. So if we have spot out of our sample, that means we have crystal. But if we do not have spot, actually, even though we mounted the sample, it may not result in spot pattern. It may result in some rings, some blurring. Then we can say we do not have any crystal sample. So by having this kind of spot out of crystal sample or simply sample, there is the evidence of having crystal sample. Okay? That concept is really practical when you mount the sample and checking crystallinity of your sample. Unless you have spot like this, your sample is not crystalline. Your sample either can be amorphous or can be very purely diffracting powder-like sample. Anyway, not a crystal. But if it is crystal, you have symmetry along ABC direction, so-called translational symmetry. Always, as a basic symmetry of crystal, simply, we can take any crystal sample initially as P1. This is about P1. So my answer was, technical term is P1. Any crystal has P1 symmetry. So if you have higher symmetry or extra symmetry upon P1, we should choose other symbol. But basic is P1. Symmetry of any crystal is, in crystallographic terminology, P1. P1 means one means no internal rotation symmetry. But external to unit cell, we have periodicity along ABC. The letter P here stands for primitive. But even very primitive, very primitive in P1 still has symmetry along ABC. Okay? If you understand that point, you have qualification in structural biology for protein crystallography. Okay? You do not understand Fourier transform itself, you do not understand reciprocal relation itself, but you need to understand this concept. Translational symmetry present in any crystal. Because of that translational symmetry, simply multiple copies with regular packing, we have diffraction. Otherwise, we may have scattering without spot-like character. So if we have spot-like image, that means we have crystalline sample. Okay? It has direct importance in crystal screening or sample screening. Although by our observation it looks like crystal, it may not be crystal, or either it is a crystal of very poor quality. As we talked about resolution, here down there we have very rough image, even without having this kind of spot-like pattern. Still, 3 angstrom, we have some spot-like pattern, but down to 10 angstrom or down to 100 angstrom. Think about this. 100 was unit cell length. Down to 100 angstrom, actually we do not have any periodicity along ABC. We just have some rough correlation in molecular, not packing, but molecular distribution, so-called radial distribution of macromolecule. under such a limit, actually we do not have any periodicity. Okay? So if you have spot-like character, we have crystal. But unless we have spot-like character, it does mean we do not have any periodicity around ABC. So evidence of like these diffraction spots or these diffraction images, we have crystal. Bottom line is symmetry at least P1. Okay? That should be your understanding. And now we have something more in terms of reciprocal. But distinguish these two, Fourier transform pair and reciprocal relation pair. As I told you, Fourier transform pair, when you are told about Fourier transform pair, you should bring two functions. What are those two functions? This time, wait. And you can say one of them and we can say the other one. Who will say first?
Electron density.
Electron density. What other do you have?
And fraction structure.
Good.
Fraction data.
Diffraction data or structure vector. They are somewhat equivalent but not very exactly equivalent. Okay? But you can say diffraction data because diffraction data itself from experiment. Structure vector is something little bit more. To be precise, it has phase angle. But diffraction vector may not include phase angle. In terms of symbol, structure vector is FHKL, set of FHKL with the given HKL listing, but structure vector, diffraction vector is amplitude or magnitude of FHKL. And what should you have in reciprocal relation in crystallography? You should have two pairs. One pair, the other pair. You will say both.
ABC and A star B star C star.
Yeah, that is simple. And here we have A, B, C. And any position can be described in terms of A, B, C, right? Along A, along B, along C. Here many vertices are explained. Here particularly 1, 0, 0 is just at the end of A. 0, 0, 1 is at the end of C. 0, 1, 0 is at the end of B. Inside of unit cell, we will have fraction of such a 1, 1, 1. Here, it can be said half 0, 0. Here, 0, half 0. 0, 0, half. Correct. But P1, P2 is kind of general position, and it can be described with the fraction of A as X, fraction of B as Y, fraction of C as Z. So with the bearing X, Y, Z between 0 and 1, it's called fractional coordinate. Inside of unit cell, any point inside of unit cell, it can be fraction of ABC, so-called fractional coordinate. Okay? But beyond or outside of unit cell, it also can be described. Any point outside the crystal can be described. Multiple of ABC or multiple of ABC plus fraction of ABC. Here, for example, if you have P1, we may have equivalent point of P1 translated along A. Then if the position of P1 is XYZ, translated P1 inside of this dimension or this cubicle, it's not a cubicle unless it is cubic. Let's say, what is the general word for such a triclinic setting? Parallelogram or? I forgot the name.
Rectangular.
Rectangular is two-dimensional word. You may have something else. This is first unit cell, default unit cell. This is translated unit cell along A, okay, between 1 and 2. Then we have P1 translated along A, and its coordinate will be what, Muhammad? If we translate P1 along A, around this position, so you should describe in terms of X, Y, Z.
1, 0, 0, X, Y, Z.
1, comma, 0, comma, Z, or what did you say? If P1 is called X, Y, Z, if P1 is translated along A,
1x, 0y, 0, 0.
1x, 1x, 1x. Here, let's say we have X, Y, Z is P1. If you translate such a X, Y, Z or P1 along A, this is 1 and this is 2. We have P1 translated. Then you have coordinate triplet. Y and Z will not be changed. So Y and Z same. Then what will be the X of translated P1 along A?
1.5.
2.
You said 1, but 1 is here, 2 is here.
1.5.
1.5.
It's not 1.5. Why do we have half suddenly? I'll give you answer not to be confused further. Simply x plus 1. Okay? If you're moving along B, it can be x plus y plus 1 and z. So we can describe any equivalent point using x, y, z. We just need to add something along A, B, C with a multiple of 1, not half. If you add half, for example, saying here, for the given x, y, z, if you add half rather than 1, x plus half, y plus z, we will not move P1 here, but we will stop here. So this one may not be the equivalent position. So to have equivalent position, we should add either on x, y, or z with the multiple of 1. Nothing else. Also, we should not mix x, y, z. For example, x, y, z in general term. I'm talking about P1 translational symmetry. Only x, not to be confused in 3 dimension. X. This is 0 and this is 1. And along x, we may have multiple copies of unit cell. Let's say 1, 2, 3, 4, something, up to billion, or at least 10,000, as we suggested, over 10,000. Okay, 10,000 copy. You have some breakdown here. Then, if you have general x, not necessarily have cross to 0, say, then this position will be equivalent to x plus 1 here, x plus 2 here, x plus 3 here, up to x plus 10,000. Oh no, 9,999. Beyond that, we may not have any more in reality. In theory, either we can infinite minus infinite plus, but in real sample, starting at the surface and reaching the other surface to surface. Okay. But for simplicity, we will not talk about real limit of such a periodicity. For simplicity, we are taking such a limit as infinite. But in reality, we have real sample with finite dimension, so we have some finite periodicity. So actually, it's not periodicity over infinite ranges, but still periodicity within such a huge ranges of unit cell in one dimension along A. Okay. So if you add multiple of 1, simply integer, they are equivalent position. Likewise, along B and along C, in general, for general position X, Y, Z, in terms of ABC, let's say electron density of rho is equal to any X plus H, not to be confused with small h, let's say big H. Both are not good, sorry. H, Y plus K, Z plus L is equal, where H, K, L are integers. You should get this point in your mind. So always basic symmetry of any crystal is P1. P1, 1 means no rotation symmetry, no internal symmetry within the unit cell. But still, we have primitive symmetry. Let's say primitive. Basically, the term primitive is for non-centering, but we can say primitive translational symmetry between unit cells. So here, integral displacement along each axis or each vector will result in equivalent position. I did say equivalent. Equivalent position. So-called symmetry in crystal. Intrinsic symmetry in three-dimensional crystal. Okay. Although these symmetry are present in crystal, we are not very interested in this symmetry. Why not? Most cases we are not interested in symmetry. That's a topic of this teaching and education paper. Although crystallography is interdisciplinary and it's overlap with natural science of physics, chemistry, and biology, yet rather hermetic, and the language of crystallography is not really difficult, but it is very exact and must be learned. What was my question beforehand, Muhammad?
Why we don't consider this symmetry inside the crystal?
Yes, that's what I told you. Not to confuse you, I'll give you answer. What is your primary concern when you are doing protein crystallography? Is that symmetry or is that something else?
Oh, it's structure.
Oh, that's it. Bingo. You'd like to know structure, not the symmetry of crystal. Translational symmetry is artifact of your sample, not your primary concern. So, most cases we are not interested in translational symmetry. Even dimeric or higher oligomeric structures we may have as a part of quaternary structure, such a higher dimension, higher, how can you say quaternary? It's not a dimension. Higher level assembly is not about translational symmetry, but it's about rotational symmetry in most cases. So we may be interested in rotational symmetry of our sample. Dimeric structure, tetrameric structure, even dimeric structure have some implication in terms of its function. But such a translational symmetry in most cases not related with biological function. So we may not be interested in translational symmetry. Translational symmetry is an artifact for crystallography. Okay. But without understanding such artifacts, sometimes it's not possible to understand something difficult in terms of complexity of any interplay between such translational symmetry and rotational symmetry sometimes matters. That part I'll not talk about this, but that is for something else. Anyway, let's go back to basic. Here another thing. Now we are looking at some pattern, not only in terms of ABC, but in terms of HKL. That's a little bit complicated, but here small HKL as an index of plane. What are you looking at? First figure. What can you find?
H is 1, K is 1, L is 1.
And with such
Along ABC.
edges, 3 edges, what do you have?
1, 1, 1. 1 along A, 1 along B, 1 along C.
So along A, we are pointing this edge or vertex. Along B, we have this edge and this edge. And with 3 points in space, a plane or one plane can be defined. Here, this is not how can I say? This is not a vector. This is a plane. This is a plane. This is vector, another vector, another vector, 3 vector. At the end of each vector or each position, we define plane. So here with parenthesis, number 1, 1, 1 and parenthesis closed given. So as a result, we are talking about plane defined by 3 points. Then this is so-called plane symbol. This is kind of extra now. Here, figure 548, lattice planes in 3-dimensional space. So we will talk about plane. How the plane can be defined from your anyway, this is plane. So what do you find here?
This is another plane.
Yes, another plane.
H is 0 and K is 1 and L is 0.
How can you understand and this and this? This is simple.
Yes.
At the edge of this is 3 points define a single plane. Here we have some difficulty. What kind of difficulty do you have in terms of understanding these two?
B is 0, but B is written first.
Even here we have 2 planes. Here we have 1 plane. What they are trying to explain to you. This this is something new to you. We are introducing concept of plane, crystallographic lattice plane, simply lattice plane in crystallography.
They try to show the reciprocal space.
They're only attached to one surface. Like that one has edges on each surface, but here it's only one, so that's why it is one. Here it is attached to two surfaces, like that.
You are introducing further complexity. Here, 0, 1, 0, single plane is given. Here, 0, 1, 0, two planes are given. Again, 0, 2, 0, three planes are given. Now Saba is talking about this one, but still, even these two figures, we are in trouble in terms of figuring out the meanings. So for the time being, let's focus on these two. First of all, I told you 1, 1, 1 plane is defined by A comes here 1, B comes here 1, C comes here 1. Then here 0, 1, 0, A
Stays here.
0,
0.
but A0 is here,
Yeah.
right? And B1 is there, right?
Yeah.
And C0 here. A and C collapsed to origin. And C is there. So it should be here.
On the
Not here.
Oh, they show the negative side also. Minus negative A, negative B, negative C.
Yes, something like that. But anyway, imagine this way. I'm not talking about the way we should understand this, but I'm challenging you as a first learner. If you are given with this textbook, assume that you are learning the textbook by yourself with the help of mine. And you will have some troubles unless you ignore some details here. So how can you figure out the meaning of these presentations? That is challenging for you to understand or simply to decode this kind of diagrams or this kind of presentation. But now I'm here to help you understand the meaning. Like a symbol 1, 2, 3, 4, 6. Actually, these are very simple ideas. But unless you are comfortable with this kind of presentation, even though the idea is very simple, you will have difficulty to understand the meaning. That's the point I'd like to share with you, and that's the point, the very point I'd like to help you. Even more here, some tilted one. Minus 1, 0, 2, minus 1, 0, 2, minus 1, 0, 2. Three planes are given in different locations. But I'll not explain this right now, but this is kind of exercise today, mental exercise. And you have this figure in your textbook, and we will come back next time with this figure, but right now I'll give you an answer. Like we love, like driving. Driving is very simple in terms of speed. First of all, we should keep the speed according to traffic regulation. In highway, in Korea, mostly maximum is 100 kilometer. In urban area, maybe under 80 kilometer or 60 kilometer. Even in Kaiste area, it should be under 30. Oh yes, you are correct. speed matters in terms of traffic limitation, but also handling, right turn, left turn, straight, going straight. Likewise, it's not about difficult engineering issues. It's not about difficult physics issues. It's about simple geometry like handling, steering, changing the direction. It's very like changing the direction. Here, this is not about rotation symmetry. This is about actually application of translational symmetry. Okay? So, this is intrinsic for all kinds of crystal, not specific to higher symmetry crystals. Okay? So, like steering, right turn, left turn, going straight. Depending on curve, you need to adjust yourself. You should steer your handles accordingly. Okay? Likewise, this is about steering in driving, changing the direction in crystallography. What direction should we change? Now I'll talk about. But I will skip this for your benefit, and I'll promptly jump to here. Okay? When we are talking about scattering, now from symmetry to scattering, with the basic symmetry present in any kind of crystal. What is that? Muhammad again. What is basic symmetry in crystal? Translational symmetry along ABC. The reason why I'm sticking to ABC was because of the diagram I presented. Parenthesis HKL parenthesis. Okay? So ABC has connection with HKL in terms of plane definition, and now scattering. Okay? Today we will focus on P1 geometry, nothing else. P1, 1, and crystal. Here, any scattering, like any crystal, any scattering has X-ray, not necessarily X-ray, any beam. We have neutron scattering, of which theory is compatible or identical with X-ray scattering, except scattering vector itself. We have neutron scattering vector and we have X-ray scattering vector. Depending on the nature of beam, either X-ray or neutron, we have different scattering vector, but still we have same geometry, diffraction geometry or scattering geometry. Here we have incident beam called S0 vector, and we have some diffracted beam this way. With respect to incident beam, we have tilt angle 2 theta or scattering angle 2 theta. And if we cross to some object, in this case electron itself, we have some tilt or scattering, then we have some observation. If you have crystalline sample, such observation will result in spot-like pattern. If they are not crystalline, simply atoms or electrons, they will have some continuous distribution. And let's suppose we have some continuous distribution, not continuous distribution, but periodic distribution, so-called crystalline, then we have pattern of crystal nature, and I'll skip this one. What did I talk about? I forgot the point. Sorry. Scattering. So scattering symmetry.
In the crystal, if we have don't get the spots, there are atoms and electrons, neutrons, but we didn't get spots.
잠깐 포즈 해주실래요? Let me go back here. I tried. This one. I started this. 다시 시작해 주실래요? We started from this figure. Intrinsic symmetry in any kind of crystal is P1. Here we have A, B, C alpha vector and corresponding plane. So-called in general, here 1, 1, 1 plane, 0, 1, 0 plane, 0, 2, 0 plane, minus 1, 0, 2 planes are drawn. But generally, we can talk about HKL plane, any integer. Okay? That's the point I'd like to explain. Here, specific planes are given, but any HKL in integer can be scattering vector. And now, jump here. Here, scattering, Fs. Now, I'm safe. I wrote something and I'm recovering my strength. Fs, function Fs, or structure vector Fs, can be described in terms of HKL. But here, without periodic arrangement of crystals, in this presentation, just electron cloud. HKL may not be integer, can be general to describe continuous distribution in 3 dimensions. In this case, diffraction pattern may result in non-integral number here. HKL non-integral, simply general number, real number. But if you have crystalline sample at the sample point, HKL will result in integral number. Let's say 1, 0, 0, 0, 1, 0, and 0, 0, 1, and multiple of them in many ways. Any combination here, like here. So we can say IHKL or FHKL. FHKL, like here. So here, if we say Fs, actually we are talking about FHKL as we had for Fourier transform, and FHKL are diffraction pattern of crystalline sample if HKL are integral numbers. Also, rho electron density can be described in general vector, position vector R, but R can be described in terms of XYZ relative to ABC vector, but XYZ is fraction of ABC. So these XYZ are not integral, unlike HKL part here. But still, rho R or rho electron density XYZ can be described in terms of this kind of translation, but they are only valid for crystalline sample. So scattering geometry is for general physics, but scattering geometry for crystalline sample has unique characteristic in terms of symmetry in electron density and symmetry result, not symmetry itself. Here we have symmetry of translational, but there, FHKL, we do not have such a translational symmetry. Existence of symmetry in reciprocal space will not result in symmetry, translational symmetry in reciprocal space, but integral numbers of HKL in diffraction data. That's the point of symmetry relation, symmetry aspect of scattering geometry. Here, scattering geometry itself is not about symmetry, but I introduced result of translational symmetry in scattering geometry. Result is like this. I'll repeat again. If you have symmetrical sample along ABC, then we will have integral diffraction pattern in HKL. Otherwise, unless we have symmetrical arrangement along ABC, that can be either electron or simple atom or single unit cell, not crystal. In such a case, it's not just a unit cell, but just single component of protein and molecule, then we will have continuous scattering. That is the result. Okay. So let's keep hold. Let's come back here. And today we didn't talk about higher symmetry of monoclinic, orthorhombic, tetragonal, trigonal, hexagonal, cubic. That is the topic of this educational paper. But I talked about point group 1 and P1. Point group 1, you can regard point group 1 as a single protein molecule of your interest, or some arrangement of such a molecule into multimetric. But from 1, we should talk about P1 if the sample is crystalline of more than billion copies of such a unit. Then we can have diffraction pattern on HKL plane, and that's what we are talking about here. Here, we are only talking about some specific number of integer HKL, but that can be general number HKL, starting from minus something up to plus something. Here, if you are talking about hundreds of angstrom, such indices can be from minus 100 up to plus 100 within some with the given wavelengths. We will not talk about such ranges, but with the help of Bragg equation I didn't talk about, you can calculate such ranges. Maximum H, minimum H, and maximum K and minimum K, and maximum L and minimum L, negative, positive. So with the varying HKL, we can imagine plane defined by such numbers, 3 numbers in integer. So we can define such a plane with the help of ABC. So for general HKL, how can you define such a general HKL with the help of vector ABC?
Integer plus a plus along that side x or y.
Take lesson from 101.
Along ABC.
To construct plane HKL. Here,
HKL, just HKL, 1, 1, 1.
this is 101, but we are not talking about 111 plane, but I'm talking about HKL plane. But HKL are not fractional numbers, are not real numbers. HKL should be integral numbers. How can you define, or how can you construct such a HKL plane in terms of ABC? That is my question to you, and that is first step for you to be eligible or valid drivers in crystallography. But that is very simple in concept. It's even simple for elementary school students can understand. I I told you that should be very simple to define HK plane in terms of XYZ.
So we should increase x plus multiple of integers. Multiple of x plus multiple of integer.
That is nothing with X. That is nothing with Y. That is nothing with Z.
Along A or along B or along C, we should.
Along A, B, C, when we try to construct electron density, it is something with X, Y, Z. But we are not talking about electron density, we are talking about scattering. Also, plane perpendicular to such a scattering. So, we only need to use integer HKL with the help of vector ABC. Very simple.
Arbitrary position from origin, like we choose it from the origin.
Yes, we have origin and we have three vector ABC. So that is nice point, very good point. In terms of origin, when we talk about ABC, we should have origin A, here B, C. First of all, we should have origin. Okay, then as an integral HKL, this case just one or none. We may have something more. Let's have shorter ABC. This is too small to explain the concept. A compatible with that diagram. B, C upside. Okay, ABC. If we have one or none, this way, 1A, 1B, 1C connect each other, then one or none plane. My question was like this: how can we construct general HKL, not specific to some number, saying HKL, but HKL as a general, not one, but larger than one, let's say. Then let's take, for example, 2A, okay, 2A. And here, 3A and 3B. And here, 1, 2, 3, 2, 3, 4. 4C, okay? Then how will construct 2, 3, 4 plane?
We will take 2 along A, the point, and 3 along B, and 4 along C. And
We already took 2A, 3B, and 4C.
And then connecting these 3 points.
Yes, connecting 3 points.
And it will become 2, 3, 4, 5.
Okay? Simple. Nothing else. Very simple. So, for general HKL, this is specific to 2, 3, 4. General HKL, we just take multiple of A, multiple of B, multiple of C, and connect them. Then it will be plane. Okay? With bearing HKL, even we can say plus 100, plus 100, plus 100, depending on the length of ABC. Minus 100, minus 100, minus 100, depending on the length of ABC, also depending on the wave, our choice of lambda. This is about Ewald sphere or limiting sphere, which I didn't explain today, but you can read textbook. But first of all, like a steering or handling in driving car, we are changing the direction in scattering. This is a little bit complex in terms of conceptual, but once you understand this complexity, this will become simplicity actually, because we are thinking in terms of dual space. The reason why crystallography is so peculiar or uncomfortable at first hand is like this. Concept is very simple, but we are operating two entities. One is real space, the other is reciprocal space. But real space is not imaginary space. They are connected to reciprocal space is not imaginary space, but this is kind of twin or pair to real space, of which length is reciprocal to original one. And physical process is connected through the concept of scattering, and concept of scattering is explained in terms of refraction. I'm talking about refraction. Scattering is physics concept. You may not be easy with the concept of scattering, but concept of refraction is common experience when you look at something. Mirror. So with the mirror, we have incident beam and we have refracted beam. So mirror is our common experience. So refraction is easily understood by you under the light of with the help of mirror. Okay? So refraction is simple concept. Scattering is physics concept. Physics may not be easy, but mirror or refraction should be easy. Now we are talking about HKL plane as a mirror or refraction plane in diffraction. As I told you, diffraction is a special case of scattering. Diffraction can be explained with the help of this kind of refracting plane. Okay? So such a refraction plane is not necessarily something special like that or those, but general like this, HKL bearing from minus up to plus. H minimum, H maximum, K minimum, K maximum, L minimum, L maximum. Total, it can be kind of sphere with the given resolution as we had at the beginning. Here, that is two-dimensional concept. Circle, circle, circle. In reality, if still above is two-dimensional presentation of electron density, but if we have three-dimensional representation here, likewise we have three-dimensional data in spheric form, sphere, with the bearing HKL. Here, only H and K may be buried, or H and L may be buried. But in reality, as a total data in three-dimensional diffraction space, we should vary all HKL with the given radius of such a sphere. Such a given radius sphere is resolution in angstrom or reciprocal angstrom. That is the concept of resolution. Okay? So here, such a concept is not well explained, but I brought such a concept at the surface, kind of exposure or revelation. Okay? So first come back here. Let's come back here. Plane. Here, even 0K0 can be understood in this way. K, we can take any K, like 0 to 0. Okay? But here, actually 0 to 0 is like this. This plane. Okay? We can construct plane parallel to this one, but here, take notice this. 0, 1, 0, simple. We take this amount. Along A and B, along A and C, nothing. Only along B, 1B. We take this one. But here, if you take my advice in terms of constructing HKL, we should take 2B. Okay? Then here, plane here, and plane there. But in this presentation, we have more in between. even here. So spacing of such a HKL plane is actually half, not double. Here, spacing is 1 unit cell, 0K0, but spacing is reduced down to half rather than double. If you follow my advice, even you suggest, Muhammad, we should take 2B for this case, nothing else along AB, AC, so we should have plane here in terms of 2B, 1B and 2B. We should have plane here and nothing else, but in reality, spacing is reciprocal. Okay? Spacing is reciprocal. Spacing between equivalent plane is reciprocal. If you have, for example, if you have general 0K0, we will take 1B, 2B, 3B, and multiple, then KB up to here. Then plane within unit cell is like this. We have total K plus 1 plane. If we discard this one, we will have 1, 2, likewise 1, 2, 3, 4, 5, 6, up to K. 0K0 will be here. And we have equivalent K times plus at the origin extra 1. Okay? If you consider or construct the plane this way, general 1, specific 1, 0, 1, 0 can be understood likewise. Here, actually 1B, this is the result of construction, our construction. This is kind of extra at the origin. Okay? Likewise, minus 1, 0, 2 can be understood in such a way. And that will be your real exercise in your intelligence, and that's all. Nothing else. Construction of reflection plane in crystallography is like taking multiple of ABC and joining 3 points. Nothing else. But what is not explained well is like this. How do you connect such a plane with the point? Point here. We have several points here. We can count HKL. This should be 0, 0 in terms of HKL if you look at A, B. 0, 0. Then crossed one can be, if you take this way, 1, 0, here, 0, 1. And increasing K, increasing H, this dimension L. Okay? Now you have such a mental construction of reciprocal space or diffraction data in integer. Okay? Such a plane, such a point is connected to this kind of plane. That is the trick of Bragg. Father Bragg and son Bragg. Bragg is feminine name, B-R-A-G-G. That's the name given in scattering angle here. Scattering angle. 2 theta is so-called Bragg angle. Theta is called Bragg angle. So this theta has something with a resolution. This is so-called Bragg angle, and the spacing between equivalent planes are this one, and this is so-called resolution in crystallography in angstrom. This star is reciprocal resolution, but they are used interchangeably in terms of usage, but they should be reciprocal in terms of numbers, also reciprocal in terms of unit. But here, such a resolution is related with scattering angle theta or Bragg angle 2 theta. Also, it has it should be changed. Resolution should be changed with wavelengths too. So 2 theta or theta and wavelengths has something with the bearing D. So back to original one. Oh, here, when you talk about diffraction experiment, we are talking about this data. But this data should be collected in the manner of bearing HKL with the given resolution D, not D specific D HKL, but as a radius of D for the sphere. Okay. Then within such a sphere, we can have variation in HKL between maximum and minimum, also within the radius. Then we can do Fourier computation. We will have electron density. Then with the bearing radius of D or bearing quality of resolution, we will have different electron density. Okay, that's what we had at the beginning. Also, what is hidden in terms of discussion is crystallinity of this sample. Without having crystallinity of your sample, we will not have this kind of spot nature. We will have some continuous distribution. But once we have spot-like HKL data, HKL intense data, it guarantees, it confirms that we had crystal sample. Then we can do Fourier transform and we will have electron density and we can do model building. Always we have intrinsic symmetry external to unit cell. What is that? Muhammad again.
Translational.
Yes, translational symmetry. Always we have translational symmetry and space group, minimal space group is P1. Okay? But in diffraction pattern, we have more in terms of symmetry. Not only translational, but also we have something extra always. What's that? Guess. At the beginning, we talked about something extra.
Rotational.
It's not rotation. We are talking P1 and its corresponding Laue group, technically saying Laue group. Let's conclude with this table again. Today, we didn't learn anything above here. Monoclinic, orthorhombic, tetragonal, trigonal, hexagonal, cubic, we'll talk about next time. But we only talked about triclinic as a general case in crystallography and space group P1 and its intrinsic symmetry of translational periodicity along ABC. As a result, we have diffraction pattern. Actually, we are starting with diffraction pattern rather than crystal symmetry. So we start with P1, 1 bar, and 1 bar meant what?
Integral
In the reciprocal space.
We talked about meaning of M, meaning of slash, and we talked about also meaning of bar. What is the meaning of bar in this symbol is my question to you, to remind you.
Reverse.
Inverse.
Inversion. That's correct. Inversion. I told you at the beginning, Laue group is the symmetry group of diffraction data, and space group here, chiral space group is space group, real space and symmetry of crystal sample. Crystal sample symmetry, diffraction data symmetry, simply saying, okay? Crystal symmetry, we have P1 as a starting point. Diffraction symmetry is not 1, but 1 bar. That's what explained here. Central symmetry, I forgot. Yes. Central symmetry of reciprocal space. Actually, if you consider DHKL and HKL plane, we cannot distinguish HKL plane and minus H minus K minus L plane. I'll not explain this fact further, but actually it's very intuitive and it's very simple, like this construction. But in mirror we cannot look back. Mirror we can use only one side, but this refraction plane is not made of mirror. This is made of atoms or electrons. So we can see sample on both sides. Both sides can act as a refracting plane or refraction plane simply. So IHKL and I minus H minus K minus L should be the same. This is kind of result. You can think for yourself. Today we covered P1 and secret of its external translational symmetry, but we didn't talk about further about anything else in terms of monoclinic, orthorhombic, tetragonal, trigonal, hexagonal, rhomboedral, cubic. But with this basic knowledge, next time, how many chiral space group do we have in protein crystallography?
65.
Where do we have 65? At which page?
Key concepts.
Key concept. 60. So if you count the rest column, here we'll find 65 or 64. What was your answer?
65.
65. Here you will find total 65 cases in terms of symbol, unique symbol. Here you will have 11 Laue group. Am I correct? One from triclinic, the other one from monoclinic, orthorhombic also one, but tetragonal we have two. Here this is mistype. 4 over MMM. Okay, here 3 inversion, 3 bar 1M, 3 bar M1, they are distinct from each other. 6 over M, 6 over MMM, 3 M bar, M3 bar, M3 bar M. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I make some error here?
Total
12? 12. Okay. I made something wrong. So 12 Laue group and 64 space group. 64, 5, I'm sorry. So here I'll give you some advice in terms of decoding meaning of Laue group and space group a little bit for you to read the paper. Is it okay to read it? Yeah. Here, 1 bar, simple, but 2 over M. I'll explain something 2 over M. 2 of M is like this. Standard symbol for 2 of M is like this. 2 over M. So rotation axis and mirror plane is perpendicular to two-fold rotation axis. That is the case of 2 over M. So this bar or slash means perpendicular to. That's the meaning of this part. This 2 over M can be written in this way also. And meaning of this is perpendicular to. Two-fold axis is perpendicular to mirror plane, or mirror plane is perpendicular to two-fold axis. Also, 4 over M, 4 over MMM, same. Also, 2 over mm, something wrong here. 2 over mm should be, actually 2 over mm can be written mmm, and in full term 2 over m, 2 over m, 2 over m. Firstly 2 to 2. Here triple 2 means 2-fold the axis along A, 2-fold the axis along B, 2-fold the axis along C. Then 2-fold the axis along A, 2-fold the axis along B, 2-fold the axis along C, and perpendicular each other we have MMM planes. So triple symbols can be understood with respect to ABC, but here something else. 3 bar 1M and 3 bar M1 have some uniqueness due to non-orthogonal nature of hexagonal and trigonal. Here 120, so something tricky here. Okay. But basically, per symbol are 2 of m. 2 of m. If it is written in full term, 1, 2 over m, 1 in unique b-axis. As a standard setting, beta non-equal to 90 degree, other angles alpha, gamma 90 degree. So this is so-called unique axis B. So in full term, 2 over m can be written in this way: 1, 2 over m, 1. If we write P1 or 1, it can be understood 1, 1, 1, although we are not writing in this way. No symmetry along B, no symmetry along C, B, no symmetry, no rotational symmetry along C. Also, that is my explanation about Laue group. And also in space group, you may find something unusual with subscript. That is so-called screw axis. Next time, I'll talk about screw axis together with full meaning of these two columns. Okay? Under the light of data collection, we are not using these symbols for theoretical consideration. We should use these symbols for data collection, okay, or interpreting the result of data collection, and to determine crystal structures out of our diffraction data. That will be next topic. Okay. What questions do you have now? You can ask any question in terms of terminology or in terms of your intellectual difficulty to follow my discussion. Even in terms of English, in textbook and in the paper.
I missed that point. Is how is it written? 1, 2 over m and 1. How is it?
1 for A, 2 over m for B, 1 for C. That's what I wrote. So unique B setting. In terms of symbol in Laue group, in terms of symbol for space group, basically we have rotational symmetry part as well as its corresponding axis. So we have 3 axes in 3 dimensions, ABC. So most part can be understood with respect to axis A, axis B, axis P, C. So up to from triclinic up to more orthorhombic, they are orthogonal and they can be understood with 3 axes explicitly. Here, they are not explicit in terms of ABC. I was explicit about in terms of ABC. For A, for B, for C. A, B, C respectively. This is valid from triclinic up to orthorhombic, but something tricky in tetragonal, trigonal, hexagonal. Not very tricky in tetragonal, but tricky in trigonal and hexagonal. But in terms of basic component of space group symbol and Laue group symbols, they are composed of letter symbol and number symbols as well as letter symbols like M. And further then, we just have inversion as a bar symbol and subscript as a screw axis symbol. I didn't explain the difference between rotation axis and screw axis, but you can figure it out for yourself. It's like learning alphabet. Here, based on number 1, 2, 3, 4, 6, and letter M, and symbol bar and slash, we derived all 12 Laue symbols. Here, based on centering symbol or primitive C-centered and I-centered and F-centered, here we added something extra with numbers and subscript. We derived all 65 space group available for protein crystallography. That's all, nothing else. So just be familiar with those symbols and you can understand what your colleagues or your structural report are talking about. No secret. Before this, you may have difficulty in terms of decode crystallographic report, so crystallography can be regarded as a peculiar science or uncomfortable or hermetic mystic science. But now you should be able to decode what the symbols mean and what your colleagues are talking about or what the structural report are actually reporting, or even supplementary material for crystallographic data really explain or talking about. Here, in terms of correspondence, anyway, you have textbook and copy. Try to match Laue group symbol and space group symbol. Then you can find some rules. Okay. Such a rule we'll talk about next time. But the rule we found today is like this. Here, P1, we don't have P. And 1 became 1 bar. So we are losing translational symmetry to diffraction data, but we are adding inversion in diffraction data. Two changes. One is addition of inversion, the other is losing P. Okay. Likewise, we have such a correspondence in the following rows. Okay? Nothing else? We are done today, and thank you.